Greetings, friends. Let's start with today's point. We will be focusing on certain aspects in predictive analytics, which is how do we predict a specific value which is continuous in nature. And when we try to predict a continuous nature value, continuous data type value, the probability associated with that value will be zero. This is because for a continuous data, we have infinite possibilities. So it's not possible for us to estimate the probability associated with that value. So if the chance of a specific value's occurrence is zero, then how we can say that this specific value may occur in future, right? So we are contradicting these statements here. One is we are trying to predict the value, and at the same time we are also saying that the chance of that value's occurrence is zero. So this is the specific point that we are going to target today. In our last session, we discussed about how the continuous random variable will be processed, especially when we want to try and estimate the area under the curve. In order to do that, we first map it to Z. The default assumption is that X is normally distributed. It is a continuous random variable, right? So we by default assume that this is normally distributed. And based on this assumption, we try to standardize the value of X to Z. Of course, we will have to verify using normal QQ plot or statistical solutions on whether this X is normally distributed or not. That is one thing we have to check, right? QQ plot can be used in simple terms. But once we detect that, yes, this is normally distributed, then we apply standardization formula. This basically will allow us to map the values of x-axis to z-axis. And once we have the respective value from x-axis mapped to z-axis, using z table, we will be able to identify the area under the curve with respect to that specific value. But when we are doing this, always remember it will calculate the left side portion, right? Cumulative distribution using the integrals. Always we will take with lower limit and upper limit. The integrations or integrals will be performed using lower limit and upper limit. So it will always be the left side portion. CDF, cumulative distribution function. The data is distributed and we are trying to see the entire cumulative space. Okay, it's a function which allows us to identify this total area. Right? Cumulative distribution function. All right, now moving on. We've discussed about a couple of examples, right? Some examples on inferential statistics. Yesterday also we were discussing about this inferential statistics concept. Right? Now, when we talk about inferential statistics, we will always try to infer the values for population because we cannot directly get values from the population data. But we want the metrics for population only. We call those metrics or the measurements as parameters. But whatever the data that we can obtain will be only a subset of the entire data, and the calculations that we perform on this, the results that we get are called as statistics. Using them, we try to generalize the statement. Right? This is what inferential statistics is about. Okay, now let me give you an example. Let's say what you're seeing is a bunch of people, right? Okay, this is my population. Now let's say I want you to identify what is the average salary of people in this area. This is, let's say, one area, and this is our population. Could be any area. It could be in India, it could be in US, whatever it is. Okay. So I'll give you one area and I say, what is the average salary of this group? I want to understand what kind of lifestyle that these people are living. expenditure power. Probably using this information, I would also be able to help the governments, the country, to plan the GDP. Okay. So if I give you this case, let's say we are talking about um, New York. Okay. New York. Um, all the people who are there in this country, in this particular place, in this location, right, are considered to be working in an IT. Okay, let's say uh, refine our sample space. So we are only talking about IT employees in this area. Okay. Now tell me what could be the salary of an IT employee. Standard of livings is what I want trying to estimate. You assume are residing in New York. Okay, you are one of them. And I'm asking you to do it. So what would you do? Do we have data readily available in the first place? No, right? We don't have data. So what should we do? What should we do in this? Do we have secondary data? No, right? What should we do?
Sample the data
Sample. How do you get that sample?
randomly, mostly.
Randomly?
Randomly pick the data from the existing data.
No. Who is going to tell you about their salaries? That data is not available with us, right?
Yes.
So in this case, what I'm suggesting is, see, understand the problem statement. I'm saying you have to tell me what is the IT employee lifestyle in this area. So in order to understand that, you need to get their salary details. Okay, nobody is going to reveal the salary details about individuals, right? It's against HR policies. Now you are one of them. I mean, we're talking about an entire place. We're not talking about one house or one small community. We're talking about entire big place. There are a lot of people whom you don't even know, right? So in order to analyze the situation, we see ultimately data is required. Okay, first we will try and see if secondary data is available. I'm saying it is not available. We don't have any salary information given to us. So that means this is not a choice. So what is left out then in this case? We have to resort to primary data source, right? Now, what are the examples of primary data sources? In this scenario, what could be the examples? How do I get primary data source? How would I get primary data? What is primary data here? Salary. How can I get that data?
Because I am one of the employee or a person staying in New York. Uh,
Okay.
Based
Okay.
on my salary,
Mm-hmm.
we can make assumptions and
One person. I'm asking you to do this task, and you're saying, okay, this is my salary. Hence, in this entire community, the people will have same salary. Is it?
no. So,
No, right? No,
yeah.
right? Yeah. One person, no. So what should you do?
We should collect data from few different people.
Exactly.
So
We have to ask people. What do we call this as?
survey.
You can say survey. You can say questionnaire. Okay. We conduct a survey in this locality or in this community, right? Using different channels, and we try to ask people to tell what is their IT salary. Right? We'll check whether there's an IT employee or not, and then we will say what is your salary. Okay. Now there are multiple challenges, guys, here. We're talking about collection of data, and see, collection of data itself is a very, very, very big challenge. Though I'm deviating little from the actual topic, but this is required for you to understand what will be the real world challenges in order to get the data, especially this kind of sensitive data. Okay, you conduct a survey. What would you do? You just probably go to different shopping malls, supermarkets, or community halls, and then you probably try and deploy people, or you put some link website or something, and then you keep requesting people to provide their feedback on the survey, right? You fill the questionnaire in the survey. This is what you have to do. But do you think everybody in this community, let's assume that here we have 10,000 people, do you think everybody who's eligible, 10,000 people are eligible, who fall under this IT employee category, are going to fill your survey questionnaire? If I ask you this kind of a request in the community, would you do it in the first place? What happened again? Radio silence. Please participate.
No, most of the people won't sign up. We have to provide some gift or something else with the survey, so people will participate in it. They'll get some
Yes.
interest.
Yes, this is one way. Perfect. So we'll have to lure them. We will have to give some carrot so that they get lured into it and they fill the survey. Okay, point number one. Some kind of a offer or some kind of a goodie you basically give to them in order to fill the survey. Okay, great. You do that. But now my second question. Can I trust the data that these people are filling in the survey form? Can we trust whatever the people, whatever the data that we are getting from these people is 100% accurate? Can we trust on that?
No.
That means the
No.
quality aspect is also a challenge. We cannot do much on the quality aspect, okay? But offers and goodies, there's a cost associated to it, right? What else I can do in order to get my data? What is more convenient? I'm giving you a hint. What is more convenient here? We are also trying to understand sampling techniques, friends, here. If you remember, I said there are two types of sampling techniques, probability and non-probability, right? Yeah. What is a second option that you can look into here? Alternate option. I would not say second, there will be multiple options. What is an alternate option here that we can think of? I'm talking only about getting the data.
We can collect the data from known people if some known people
Exactly.
are there.
Exactly. This is called as convenience sampling, which falls under non-probability, biased sampling. So if I have 10,000 people, if you invest money, if you spend time and conduct a fair survey, you may not get required information. Not even one person may be filling it. We don't know. Right? Even in case when you are offering some goodies for them, even then people may not be interested, especially because we are asking about their salary details. So the best option in this case is, out of these 10,000, who all people you are associated with, your family members, your close friends, you target them. Okay, first start getting information from them. Okay, again, quality aspect, as I said, you cannot trust, but at least you will have some data to proceed. Okay, is this scenario clear, friends? Again, radio silence. I'm assuming.
Yes.
Clear. Okay, great. All right, now I am asking you for a task, right? This is the task that I have assigned. Now, when I say you, I have Archana, I have Nikhil, I have Priyanka, I have Sri Kundana. 4 people are there. I am giving each one of you this task. Okay. Independently, you are independent, isolated. Assume you don't know anybody. I mean, you don't know among yourself, you don't have any kind of information, or you're not known association. I mean, you're not friends. Okay. You're completely strangers. Assume that. Now, when I'm giving this task to you people, what you do? You start doing the survey, or you try to reach out to the people whom you are very much close to, and you get some data, right? Out of 10,000, maybe you are going to get a sample of 500. I'm exaggerating, but still, maybe 500 people will respond to your survey questionnaire along with your close friends. Okay. So, what you do? You take that data, and then what you do? You calculate. What are we interested in? We are interested in average salary, which is like a representation. So I would get sample statistic. Right? I'm saying Archana is getting sample statistic, and using this sample statistics, she will make a statement for the entire crowd, 10,000 people. Okay. Let's assume this is $5,000 per month on an average. I think it's less. Let me put more realistic, $10,000 per month. Not sure if this is also less or no, but yeah. So this is basically how your salary is being represented for the entire community. I'm saying they are decent class people from an economic standards wise, because they are getting month per month on an average $10,000. This is the statement which Archana is making to me, okay, based on what she has found. Now comes Nikhil. Nikhil also followed the same process. Nikhil also, let's assume, got 500 people, and he got the average. But do you think the 500 people who Archana was having, right, the data from, do you think those will be the same set of people for Nikhil also? Both of them have same set of friends? Friends maybe, but family members would differ, right? At least. Likewise, let's say I have only 300 people for Priyanka, and Sri Kundana probably has 800 people data. Based on their locality and based on the goodies that you are providing, given the same budget, this is the kind of data you are getting. Now, each one of you is coming and saying that, hey, I employed inferential statistics, which you taught to me. Yes, that is what I have explained. Inferential statistics, right? You cannot get full population data. So you will take sample data and then process the data, get the statistics, use the statistics to infer the parameters. There's a process, and you followed perfectly fine. But do you think I'm going to get the same result from everyone? Yeah.
Mm.
No, right? Obviously, no. Maybe Priyanka is a senior executive, senior person from an experience perspective. So her friends circle would also be in the same group, right? Majority of the people will be at the same level. Maybe she has, I'm making Priyanka old here just for fun. So she has, let's say, 20 years of experience. Experience is 20 years, so she's very old. Okay. So all her friends, close friends, or family members for that matter, would also be at similar age group. Okay. Nikhil is just started his, let's say, work career. He just finished his education and he's just started. He's probably less than 1 year, or let me say 1 year experienced person. Right? So I'm just being gender biased here. I'm saying Nikhil is younger and ladies are older. Okay. Now, when Nikhil is conducting the survey, people who responded to Nikhil are in this age group, right? His friends, close friends, and family members would probably be much younger. Now, the case, what happens is the average salary representation by Nikhil would be very less compared to the average salary that Priyanka would come up and say. There's no wrong in the process. It's only the situation here which is giving us variations in the sample data. Data is not consistent. Making sense, guys? Is the situation clear now? Understanding sampling variation, that is the title here. We will perform inferential statistics only. But if in case we are doing it multiple times, or if multiple people are attempting isolatedly without, right, independently without having any interaction, then we would eventually get different answers from different people because of underlying sample is different. This is the challenge for inferential statistics. Okay, different samples yield different results. How do I overcome this? This is point number one. We will look into the point number two, which says probability of a value that you're trying to predict, which is continuous, right? It has probability associated with it, has zero. So that is point number one. This is point number two. So we'll start with point number two to begin with. Okay. I will ask you a very, very simple question. Okay. Your manager probably will give you a task. Okay. There's a project assigned, and your manager, he or she is asking how much time would you require for this specific task. ETA is being estimated, project plan is being created, so they will ask for a duration for this task. What would you say? Some task. What kind of duration would you generally give as an answer here? Any example?
It depends on the task. Like
That's what. Assume some task and give me some number.
2 weeks maybe.
2 weeks. Okay, that means we will take 10 days, working days. Yeah, anybody else? Any example? You can imagine whatever task you might want to imagine. I just wanted to see what kind of responses I would get. This is task one. Let's say this is task two. Anybody else? Based on your day-to-day activities, guys.
5 point.
Maybe a month.
Yeah, one at a time, please.
A month.
1 month, that is 30 days. I'm taking working days, so it is more than 1 month. Okay, next. Some example. It could be in hours also, okay?
5 days.
5 days. Yeah, everybody is very busy taking big tasks. Nobody is taking small tasks. Okay, good. Yeah, Nikhil. Sorry, go ahead, Nikhil.
Hours.
Sorry, pass.
2 hours.
2 hours, okay. Sorry, I heard pass. Okay. You cannot say pass to your manager, right? Okay. So now, if I am the manager of this team, okay, you all are under my team, assume. If this is the scenario, if I'm assigning you different tasks and if you're coming up with these answers, then I will not take you in my team. If your manager knows the statistics concepts, then definitely they will not, he or she will not hire you. Why? Anybody? What is the reason? This is continuous in nature. If the data is continuous in nature, then anything ringing? Answer? Anybody? You're estimating something here. What is the probability of a continuous random variable? A single
Zero.
value.
Zero.
Zero. What does that mean? There is no way you are going to complete the project in 10 days. There is no way that you are completing the project on 30 days. No way 2 hours you are going to complete the task. The chance of you finishing your given task at this stipulated time is zero. All right. So what would ideally give, or what would be the ideal scenario? So if I ask you a very another simple question. Let's say you have to travel daily from your home to office. Yeah. Again, same question. How much time do you think you will take to reach office on a day-to-day basis? Yeah, I mean, you guys are working, right? Hope you're not working in online mode.
We do work remote.
Everybody is working remotely, is it? Oh God. Okay. Okay. If in case you would have to travel, how much time do you think it will be will you require?
Again, it depends on distance.
I mean, your
And
office, right? You know, your home to your office,
30 minutes.
30 minutes. Okay. Yeah. Another anyone?
15 minutes.
15 minutes. Oh, this is nice, convenient, nearby. Anybody? Yeah, take a guess, guys. I have 4 people. Some time estimated
40 minutes.
40 minutes. Okay. Yes,
45.
oh, so Archana has to travel a lot. Okay. Okay. Now, 2 questions here. One, you already know. What is the chance of you reaching exactly at this time? 0.
Zero.
Right. But even before that, another question to you people. Why did you say 30 minutes? On what basis you are saying 30 minutes? On what basis you are saying 45 minutes or 40 minutes or 15 minutes? How you came to a conclusion of this number to start with? Probability associated with is 0, fine. But how did you come to this conclusion? That, yeah, it may take 30 minutes or 40, whatever the number is.
Average time taken.
Based on everyday's time that we
Uh,
calculate or
Based
sample.
on historical experience. Can I say that?
Yes.
So, what we are looking at historical data, and from that historical data, we are trying to represent a single value. Right? So, it is like your statistic, average, right? Past experience average. So, this is sample statistic, but we are saying this is having a probability associated with it as 0. So, how do I ensure that probability associated with this number can be made something other than 0? Say, for example, this is my value, or let's say somewhere here, this is my value, right? This is what I'm saying. It is continuous value. So this is number X bar. Let's say 30 minutes I'm taking, okay, this example. Reaching the office, I have 30 minutes. But under this bell curve, we are getting a line. Area of a line is 0. Probability associated with the single value is 0. So how can we give a value which does not have probability 0? Are you sure you're going to exactly reach at 30 minutes? You said 30 minutes based on your past data, right? But in the historical scenarios, did you reach exactly at 30 minutes on every day basis? Yeah?
No.
Oh, that's an
No.
average.
It's an average. So there may be some kind of variation in this, isn't it? If I say 1, 2, 3, 4, 5, we are saying 3 is the average. But when you look into this data carefully, we see each value has some variation associated with this, isn't it? So average is fine, but we also have to give this variation. So generally what we say, if I ask you question and how much time do you reach, how much time do you take to reach office, then you casually say 30 minutes, but you'll also say that maybe plus or minus 10 minutes or 5 minutes. I'll say maybe plus or minus 5 minutes. Generally we use that, right? Subconsciously we tell this, isn't it? If I press and say, oh, are you sure you exactly take 30 minutes? Then you may say, give or take 5 minutes, isn't it? Very casual discussion. What does this imply? What does
There
this
is a
mean? Yeah, go ahead.
there is a variation. So every day it might not take exactly 30 minutes.
Yes,
Sometimes early.
very good. Very good. That's right. So sometimes you may reach the office much early, probably because of less traffic, or maybe you're very lucky. All the signals were green when you're coming up. Or maybe you're very unlucky, everything was red when you're coming, and you have to stop at every signal. It may take more time also because of traffic may be there or road conditions may be there, etc. etc. Reasons are out of control here, right? So we cannot control them. Hence, variations are there. Now, if I break this up mathematically, if I run this, this is 25 minutes and 35 minutes, isn't it? So here I'm giving you a range, an interval. An interval. So if I try and write that on this graph, I would say 25, 35. This is 25 minutes. This is 35 minutes. Now what I do, I will calculate area under this curve, green shaded portion. Do you think the area under this shaded portion will be 0? We're talking about area under the curve, right? Will it be 0?
No.
No, right? We have already learned the calculations. Yesterday, we did some calculations where we knew what is the value here and we were trying to calculate the entire left side portion. Now we know the center portion, I mean the area that we need to calculate. We got 2 data points. So we will have to calculate probability of x2 and then subtract this with probability of x1. That gives you the area under the curve. Got it? So when you're estimating something, especially when you're talking about a continuous random variable, right? When you're estimating a value here, we will add the variation. How do we represent variation? How do we represent this variation? Statistics. How do we represent this variation? We're talking about some variation, right? This part. So from analytics perspective, from statistics perspective, how do we represent? This is x bar, fine. This is x bar. But how do I represent this?
X plus or minus mu.
Mu is average. That's a population parameter. X bar is sample statistic. How do we represent variation?
Sigma.
Sigma or sigma square, right? Sigma square is the variation. Sigma is the standard deviation. We're talking about deviation in our estimated value. So we have to bring that standard deviation into picture. Is this concept clear, everyone? Any doubts in this? Yeah, please be very vocal, guys. This is very important concept. I'm taking it very slow. Any questions in this part? Okay, radio silence. Assuming no questions, moving on. Remember whatever we discussed, okay? All right, so we are going to talk about something called as confidence interval. Not just interval, confidence interval. Okay, what does that mean? If I say 30 minutes is what we will take to reach office as an estimated value, but there may be variation. So we are bringing that variation here, standard deviation, right? Which gives me some kind of interval, plus or minus some deviation. Okay, I'll represent standard deviation with yes, not population standard deviation, but sample standard deviation, yes. Some variation. Okay. Now, when I say this would be the time that I might require, right? Your range is 25 to 35. Okay. But I may also say 30 plus or minus 10. This basically gives me what? 20 to 30, 20 to 40 range. I may say 30 minutes plus or minus 20 minutes as well. So this basically is 10, comma 50. Isn't it? I may keep varying it. Now, my question is very straight. How much time do you require to travel from home to office? You have to give me a realistic single number. Isn't it? From if I have to accept, I would need a value which is more accurate to reality. So if I draw this bell curve, if you observe this, 25 to 35 is this. Okay, let me write 25, 35. But if I take a different color, this is 20 to 40. Next is 10. This is 10. This is 50. Okay, three different colors I'm using. Now, in reality, what I need is a value which is more like this. Okay, hey, I'll take exactly this much amount of time to reach to the office. When you ask that question, right? When I'm asking you the question, you probably you're getting ready. But what I do at the time you start to office, I will record it. When the event is happening, I will start recording it. So once you reach, I will know exactly how much time you have taken. Exactly how much time you have taken, right? This is the actual value. But I'm estimating here, right? This is estimate. That means even before the incident happened, we want to upfront predict. So the actual value will be exact point, right? So I will get maybe 32 minutes. We don't know. I'm just giving you a number. All right. So if I am asking you this question, which interval would you give me? Which one would you say? 30 plus or minus 5, 30 plus or 10, plus 30 plus or 20. Which one would you tell me? Hey, let's say I'm your manager and I'm asking you for a meeting, and because there were probably clients waiting or something, escalation has happened. So I'm asking you these kind of questions. Okay. So what would be your answer?
30 plus or 5.
30
Plus or
minutes. Okay. This is Sri Kundana's option. Yeah. Others. I want everybody to answer, please.
Plus 10 plus or minus 10 because it'll have more buffer.
Okay. Very good. Priyanka says 30 plus or minus 10. Okay. Archana, Nikhil. What about you guys?
30 plus or minus 5.
Okay. Archana also says 5. Nikhil,
30 plus or minus 5.
you're also saying 5. Okay. Very good. Okay. Now, if you tell me 30 plus or minus 5 minutes, I will take this green color back and I would give you this portion. See, what does this portion actually represent is when you give this number, right? When you're giving me this number, you're basically saying that I would be reaching the office anytime between this window, 25 minutes to 35 minutes. That's what you mentioned. Okay. So that means the actual value that we are trying to see, you are saying that it will fall in this range. Now, when Priyanka mentioned 30 plus or minus 10, what did she say? Hey, this is my area. Okay. And when I say 30 plus or minus 20, the blue one. So we are talking about area under the curve, right? Area under the curve, which is representing what? Probability, which is representing probability. So you tell me the chance of the actual value falling in this green zone is more, or the probability of the value falling in this pink zone is more. Which one is more? Probability. I'm asking about probability. The chance of the value, actual value falling in these ranges, which one would have more chance? Probability associated with the value falling in that specified range. Which one has more chance?
Pink one.
Yes, obviously, you can see the diagram, right? The range also you see 25 to 35 has what? 10 values, whereas 20 to 40 has a range of what? 20 values. What does this basically mean? Priyanka has more confidence when she represents this number to the manager because we are estimating, right? So Priyanka can be more confident saying that the range is, because of the range, right? We are talking about the confidence is associated with this range. Why she is more confident? Because she has more chance of getting correct. There may be scenarios where you may take only 24 minutes, or there may be scenarios you may take 36 minutes also. We don't know. So if this happens, then the estimated value that you three people have estimated, right? That estimated value does not have the actual value. That means your estimations are wrong. isn't it? So the chance of this interval compared to the chance of this interval is less. So there is more chance of failure. Here, there is more chance of success. Making sense, guys? So the confidence is associated with this interval. Okay. Larger the range, more confident you are. What is the area under the curve? Total area under the curve? One. What is the total area under the curve?
1.
100%. 1. Okay. Now, if I want to be 100% correct in my estimations, can I say, hey boss, I will reach the office somewhere between minus infinity minutes to plus infinity minutes? He will, he will immediately throw you out, right? He or she will throw you out of the office if you give this kind of a range, isn't it? 100%, yes, I know, but there are infinite possibilities under this area, isn't it? So we have to draw a line. We have to balance this interval in such a way that your confidence is high. At the same time, this is more close to the exact value. Exact value is a single value, one value. You have to try and represent this range as close as possible to that actual value, isn't it? So there is a fine line. You'll have to try and do the trade-off and balance the range in such a way that you should not be very obvious by giving very, very large range. At the same time, you cannot take risk by giving small range, and right, which increases the chance of you going wrong in your estimations. Got it? So range estimation is again very, very critical. This confidence interval is the range interval, which is having confidence. It gives us the range in which the actual true value will likely fall. Okay. Again, is this concept clear? This point is clear? We are talking about sampling variation. Point number 1. We talked about the previous case, right? We talked about variation in the samples, isn't it? And we talked about estimating the value using statistics. This is inferential statistics. So we know that there will be different results because of sampling variation. So when we want to estimate a parameter, in this case, it is nothing but mu, we need to bring in that uncertainty into picture. So we are going to add the variation. Sorry, my bad. We are adding the variation. Okay. But this variation is also associated with some confidence. Now, how do we quantify all this? Theoretically, this is very good. We are saying 30 plus or minus 5 or 30 plus or minus 10, etc. But how are we going to quantify that? And how are we going to map that with confidence value? How much confident you are? You can either be 0% confident or 100% confident. That's what your area under the curve speaks about, right? Total area is 100%. Probability ranges from 0 to 100. So I want to quantify it. How do I quantify it? Okay. To find a solution for this, statisticians have studied a lot of things. They studied the pattern in the data, etc., and all that. And in order to find a solution, see, ultimately, I'm talking about what? Area under the curve. I want to calculate area under the curve, isn't it? And I explained previously that calculating the area under the curve contains a process. You cannot directly calculate the integration, right? The integral values. f of x dx. This is quite a trivial task, right? And laborious job, I should say. So what is the solution to capture area under the curve? We first take random variable x, standardize, find the z value, corresponding z value, and then refer to z table to identify probabilities. This is the process. But in order to do this process, first, I should be able to justify this standardization. When I can do standardization, when I can represent values of x on z, when x is normally distributed. What we are doing is we are assuming and then proceeding further. But we need to ensure that if this process has to work, then theoretically also x has to be normally distributed. Only then all this works out. Right? So all these studies happen, and we are also talking about sampling variations. Sample 1, sample 2, sample 3, so on and so forth. And here we are taking estimation 1, estimation 2, estimation 3, so on and so forth. Now, as an individual, right, when we are doing this, Archana did her calculation separately, Nikhil did his calculation separately, Srikundana did separately, Priyanka did separately. So that means you all would probably getting one sample, right? Some one sample, and based on this one sample, you are making the estimation. That means you would have a single statistic. Okay, single value. And we know that X is normally distributed. Okay, it has to. And that is what has to be proven. So we are saying that, yes, this is validated, and only if this is true, only when this is normally distributed, this is possible. That means the population, the sample data that we are getting has to be normally distributed, and then we will get one statistic. But we are saying there is a variation in those sample statistics because everybody is doing different sample analysis. So what I'll do is I will take this as data now, the statistics as data, though I will have one statistic. But in order to apply some logic, I'm assuming that we have multiple samples taken. We have calculated all these different sample statistics. Okay. So this is our data now. Now, when I look into this data, there is definitely variation. That is what we're talking about, right? There is variation. We know that this is a continuous random variable. Always remember, you take any statistic calculation, any statistic, it will always be continuous. It will not be discrete. Okay, so this is a statistic which is continuous and it is random. It is varying randomly. That means this value that we are getting is coming from a continuous random variable. That means this data should have some properties also. Only then I can analyze this data. And then we can identify some pattern and then make some conclusions. Okay. So if I take all this data and then analyze the data for the pattern and etc., what scientists have found is this continuous random variable that we are seeing will always follow normal distribution properties. That means the sample statistic data is also normally distributed, not the original data or original sample itself, but the results that we are getting from those different samples. If I take this as data and verify, this is also normally distributed, and this is exactly what is proven in central limit theorem. Okay, it states that the sample means will follow a normal distribution regardless of the original population's data. Whatever the population data we are talking about, even if it is discrete data. When we calculate statistics, all has to be numeric, okay? So your population may be non-normal data. It could be discrete data, but it would be non-normal data. Okay. Even in such case, the sample means that we are getting here will always follow normal distribution. Okay. What I would suggest is take a very, very simple example, very popular example. This is my actual data, uppercase letter, right? Assume I have numbers from 1 till 9. Assume. Okay. And what we need is this data. Practically speaking, we will not know the entire population data. Hence, I cannot calculate this. Okay. Now we are assuming that we know this data, and then we will take random samples. Let's take a large number of samples. Okay. I'll say P. Large number of samples, S of P, maybe like 1,000 or 10,000, etc. And for each sample, calculate the statistic. You do this, practically you do this. Okay. Maybe you take 100 samples or so, maybe 50 samples. But ensure that the number of samples that you're taking is greater than 30. Okay. The sample size here may be 2 or 3 or 4 or whatever it is you take. For example, sample 1 is randomly taking the numbers here. Could be 2, 6, 8, 9. This could be my one of the samples. Randomly I'm taking 4 records into my sample. And then I'll calculate average. Similarly, I'll take sample 2, sample 3, so on and so forth. So you get these statistics, right? You try to plot this data and see. What you would get is a data which looks very similar to a bell curve, where this center would be 5. So these are all different sample results, okay? I'll have 1,000 samples taken. First sample is giving me, let's say, 5. Okay, what is this giving me? This is 14, 15, 10, 25. 25 by 4. 6.25, right? So I'm getting 6.25. Like that, when you take multiple samples, you'll get one mean. So you project that mean like this, okay? When you do that, you'll find out that there are scenarios where majority of the times you get 5. Why I'm saying 5? Because the central limit theorem, when it was studied, right, we observed that this is always normally distributed because of this bell-shaped curve is what you're going to get, right? But if I take first moment business decision of this sample statistic, what will I get? First moment means what? Average.
Mean.
Right? I'm calculating mean. Mean of what? Sample means. This is sample means, right? So I'm taking mean of sample means. When you do that, you'd always get the actual population mean. Mean of means will always be population mean. Okay? And if I take the second moment is nothing but what? Your probability distribution, standard deviation, right? So the mean of sample means is always equal to population mean. And then the population standard deviation, sigma. This sigma is called as standard error. Okay, how do we interpret this? Mathematically, it is represented like this. Variance is sigma square by sample size. If I take square root, I get sigma by square root, standard deviation. So if this is my total area, sample spaces, okay? All here, I would have different samples. Okay, like this, I'll take different samples, and what I'm trying to find out is actual mean. But in order to get this, I will find sample and then I will find x bar 1. This is what I get, right? X bar 2, X bar 3, X bar 5. Like this, I'm getting different samples and calculating the averages of those samples. Standard deviation is speaking about the deviation in our estimation. Deviation means x minus mu by sigma, right? Sorry. X minus mu whole square summation by n, right? This is the average spread. So standard deviation. So here we are trying to calculate that average deviation. On an average, how each sample is different. So variation is being represented. This variation is called as standard error of mean. Why? Because we are trying to calculate mean, but to do that, we are calculating a sample mean. On an average, all these different people who are calculating these samples will have some deviation associated when it comes with reference to your actual population mean. Some variation will be there. So on an average, that variation is called as standard error. It is termed as error because we are estimating something, but we are erroring out in estimating the true value. Okay, standard because it is the average of all these errors. Okay, so this is the concept that we are trying to find out. Now, what do we need? We need population parameter. But if I have to estimate it, I will have to take a sample. But I'm trying to say that if there are multiple samples which are being computed, on an average, the deviation in this computation, in the deviation or the error in my computation is plus or minus, it could be here also, right? X bar could be here also, or X bar could be here also. And this is the error that we are getting, right? So I will say margin of error. This is error, but we'll say margin of error because we will have different error ranges, right? So some will be this much, some will be this much. Variation in errors are also there. So this is how we represent. This interval, it gives us interval, but this interval, the margin of error, is always associated with some confidence. That confidence is nothing but the area under the curve. But in order to calculate the area under the curve, we will have to basically take this area, right? We need to know what is x1 and what is x2, the range. But we don't know this value, but what we know is that x is normally distributed. We know this, right? That it is normally distributed. So what we do, we standardize. So that means we are mapping the values of x onto z. So I need the z1 and z2. Even if I can find out z1 and z2, I will be able to map those, do the reverse calculation to get x1 and x2. What I know here is the area under the curve. Because I want to follow some industrial standards and say that whatever I'm estimating, I'll give the estimations with an industrial standard, which is 95%. Okay, you cannot say 100% because remember, minus infinity plus infinity, right? The entire area will be minus infinity plus infinity range. So I would be more realistic and I will say 95% accurate. That means there is 5% of chance you go wrong. That's okay. Again, you may say how 95%? Because we are talking about minus infinity to plus infinity, that is total 100 area. If I say 95%, then almost the entire area is being covered, right? This probably is one of the questions which people will get. Okay, but if you remember yesterday's session, we talked about empirical rules, 6 sigma concept, right? So even for 2 sigma, you get around 95% accurate. 2 sigma variations. Okay. So that means I'm going to try and take the spread which is accepted in 2 sigma region, which gives me an area which is close to 95%. But yeah, don't worry. I know exactly that the portion is 95%. So whatever calculations we did yesterday with respect to Z table and all that, we do reverse calculation. I know that the area under the curve is 95%, which is 0.95. So if I know the area, this is 95% is what we are saying, okay? What will be this value and what will be this value? That's all we need. So that means this area is 0.95. And if I have to refer to Z table, remember Z table will have left portion, entire left portion represented in the table. So that means I need to look at this portion. How much is this portion? Yeah. How much is this shaded portion, guys? This is 95%. What will be this portion? What happened? This is Z.
2.5%.
Correct. Don't be in doubt. That is correct answer. This is Z, right? Perfectly symmetrical across the center. Right? Total area is 1. This portion is 95. That means I have 5% in total outside, but that 5% has to be equally divided. This portion and this portion, right? It's symmetrical. So I'm dividing it by 2. I'll get 2.5%. What does 2.5% in decimals mean? 0.025. So I will go and verify this number in Z table. Yeah, I will represent this in Z table. Let's pull up the Z table that we were looking at yesterday. (0.025). Where do you see that 0.025 number? 0.025, not 0.05. 0.25. Okay. So we probably may get confused somewhere around here. But this is not the value that we are interested in. 0.0. 0.025. 2225. It's not there here. I'll have to scroll a little more. 0.025. Where is this value occurring? This value is occurring at minus 1.9. And the second decimal is 0.6. So that means minus 1.96. So I'm getting this Z1 as minus 1.96. Now, if this is minus 1.96, what will be the Z2?
Plus 1.96.
Plus 1.96. The Z, right? Center is always at 0 and it is symmetric. So what we are going to do, we are going to add this 1.96 here with the standard error, this component, standard deviation in this calculation, right? Which is this. This gives us the actual value of mean. This mean. And we will not get single number, we will get a range. And that range will have a confidence of 95%. Okay. So we'll basically try to get the sample, whatever the sample that we get, then we do the point estimation, which is X bar, and then we try to capture the interval. which basically is given by this formula. X bar Z at 1 minus alpha. Now this is very important, okay? Point estimate plus margin of error. Point estimate is nothing but your sample estimation. Margin of error is the variation that we are getting in the computation, which is represented by this portion. We are using Z to identify the X coordinations. Both of them are normally distributed, so Z into this will also give you the right answers. Okay, Z value into standard error. That's the margin of error value. Now the alpha is called as significance level. Significance level. 1 minus alpha is representing the confidence level. Significance level means the chance probability, okay? This is the chance of going wrong. That means the portion outside the 95% area. That is given by alpha. So if I represent this like this, then this 95% which I'm drawing is represented by 1 minus alpha. Where 1 is the entire area. This is alpha by 2, this is alpha by 2. These portions, right? These are alpha by 2 and alpha by 2, which is basically total is alpha, and this portion is 1 minus alpha. It's called as confidence level. Very, very important parameter. So Z at 95% is represented with this formula. You can calculate different confidence regions. All you have to do is do the calculation for this Z value. Substitute the area 1 minus alpha that we are having, right? Not for 95%, but 99% and all that. When we do that, you'll be able to get this portion. Referring to Z table, right? For 95, we got minus 1.96 as minus Z. Why? Because here we had 2.5% area, 0.025. If it is 90%, then what would be this alpha by 2? One minus alpha is 90%. What would be alpha by 2?
5%.
5%, which is nothing but 0.05. When we check that, it comes around approximately at minus 1.645. Not 1.65, but it comes around 1.645. Refer to that Z table, okay? You need to check. And when we talk about 99%, what will be this value for 99%?
0.5.
0.0.
0.5%, so 0.005, 0.005.
Exactly. When you check this, you will get somewhere around plus or minus 2.575. Okay, so these are the standard numbers. This 1.96 is something you will have to by heart, friends. By heart it. You cannot forget this. Now, this is theoretical part. In our next session, we will try and apply this concept, whatever we discussed, to solve a business problem. Okay, this is a Z table. These are the Z values that I was talking about. You please make a note of these calculations. In fact, do the calculation, friends. Just try and do the calculations like what I've explained. Refer to Z table. Try to get this number for all the three, 90%, 95%, and 99%. By heart it.